Hello, friends. My name is Brian, aka Pen Center. We're joined this morning with our lovely co-host Zach, aka E to the 2I Pie. Zach, how are you doing, my friend?
I'm doing fine. Yeah, doing well. We're having a good time over here, and we actually got snow in Utah for the first time. It feels like all year. We've been pretty dry this year, and thank goodness for the snow. We were not part of that storm that came all the way through from the East Coast, so it's sort of nice to have something on the ground. I'm used to that.
Well, I hope you enjoy your white Christmas.
Yeah, right, White New Year, right? Like
It's a little late.
White Valentine's Day before anytime soon. But yeah, we're here to chat about tasks, and specifically something that has caught my attention over the past little while. With for those following along in our book, we've not been going through every chapter, but we're looking at chapter 8 today, and the word that I'd like to talk about, or that I think both of us would like to talk about, is the word autonomy. And when you talk about autonomy, and I actually am reminded of a TED Talk I watched some years ago from Dan Pink that says it was talking about how to motivate people, and you give them autonomy, mastery, and purpose as the three big things they need to be able to succeed in their career or something like that. And that word autonomy has always stuck out to me whenever I listen to that talk, and I listen to it on occasion. But like, autonomy is sort of a weird phrase in an educational context. Because if you think about the traditional classroom again, the traditional classroom is very much not autonomous, right? It's not its own thing. Like, students don't feel a sense of autonomy. They feel like they have to just take the notes and do what the teacher what they say and all those things. And in so doing, it creates an environment where I'm just going to tell you what to do, and you do it. And so the idea of autonomy is a bit weird to think about, right? Like, we don't often think about students having autonomy.
Yeah, and I think like you're thinking about autonomy in the sense of like being in the driver's seat for their own learning, right? Is that kind of how you're thinking about autonomy here?
That's how I'm thinking about it. How do you think about it? Like, I mean, do you have any other interpretations?
I think that's the best way to interpret what we want to talk about today.
Yeah.
Because like, I think what you're trying to say is like, and please correct me if I'm wrong, in the traditional style classroom, students play the role of being the student, right? We saw that last episode. So students come in, they, I guess, are empowered to ask specific kinds of questions, right? Like the "Am I right?" question is a very common kind of question that students want to ask. And we talked a little bit about like stop thinking questions. So there's this, I guess, notion of students looking for affirmation from the teacher who's in that teacher role, and utilizing, I guess, strategies or methods that are geared towards studenting, right, in quotations, rather than geared towards being a creator and distributor of the knowledge that's being created in the classroom.
And it's not wrong to want to know if you're right. There's a natural, like, if you're given something, you're like, I want to verify that this is correct in some way. I want to know that what I'm doing is actually being productive. I want to feel a sense of productivity. So that feeling isn't inherently wrong. But when you ask a question that has maybe only one right answer, those questions tend to lead to only one way of doing things, or like the way. And even if there are multiple approaches, a good task generally doesn't have one correct answer, though it may eventually lead to an efficient answer or some kind of, you get a good thinking task will have some kind of variation in how students think, right? And
Yeah.
and how they approach getting to a final solution.
Yeah, and I think the biggest kind of visual that I took away from like just kind of glancing over this chapter was the idea of like a distribution of knowledge. So I kind of pictured like a funnel, right? So if you're in a traditional classroom, you have the funnel, but the skinny part of the funnel is up, right? So the teacher is pouring water into this funnel, and it's getting distributed downwards to the larger part, which is the students. Whereas I think what Liljedahl is trying to do is reverse the funnel so that now you have the water being poured in this way, it's getting sloshed around all over the place. Groups are able to share the knowledge that they're creating, and eventually the teacher has to kind of get down to the consolidation piece, which is the bottom of the funnel.
Which is where we start bringing together. This is what's going to be next time, by the way, is we're going to talk a lot more about consolidation and what that means. But like when we talk about building autonomy, it's allowing students to explore. It's allowing them to try things, right? Like that's freeing when you think about it at first, but it's actually very scary from a teacher perspective. You're allowing anything to happen, and when you allow anything to happen, that you have to remove control, right? Like that as a teacher is very hard to do. it's not right. It's not like easy to say, if I put everyone in rows, I know what's going to happen, and I have some control over what's going to happen. And this is why I see sometimes in syllabi, I wonder if like, I don't want to deal with the messiness of having to deal with pen, so I'm just going to require pencil. And my syllabus, I'm going to say, okay, only number 2 pencils are allowed in this class. We're not going to allow you to use pen or do anything else because it's nice and neat and orderly. I can get everything done. And from a teacher perspective, especially in 2026, the stresses of being a teacher, you sort of want that structure, right? Like I can even empathize with that a bit.
Yeah, especially now with artificial intelligence coming into the forefront in a lot of places too, right?
Right. And this book was written in 2021, I think. And so even given the publishing date, I'm checking right now, I think it's 2021. It is. So it was published in 2021. This was published before ChatGPT.
Yeah.
Like you can think about that for a minute. Like the ChatGPT
you can tell too, right? Like there's nothing in here that discusses any form of generative AI or large language models.
No, and I wonder.
So it wasn't a problem at the forefront of what they were thinking about, right?
This is a topic for another day. But the concept of using generative AI in a classroom, I think people are starting to push away from using technology at all in the classroom. This is actually a really interesting push that we might want to talk about another time. But I know there's a book that I've been interested in reading about the digital delusion, and people are in the States are starting to push back on having one-to-one classrooms and so on. So because of a similar argument to that of The Anxious Generation. If you're familiar with that book, it's sort of in the same spirit of like, okay, well, we're almost overusing it in the classroom. But that aside, the goal here is to give students autonomy. The goal is to give them an ability to explore the problems and to take ownership of their learning. Maybe that's another way to think of this word autonomy, so that they can get the help they need when they need it, rather than having to wait for a teacher to do it. And you use the word mobilize, I think. I wonder if we start talking about in practice what this autonomy looks like.
Yeah, I think that would be the first question, right? Like, if this is something that we agree that we should be doing, how do you create that environment in the classroom? I think that would be my first question, right?
Mm-hmm. And to do that, I think what we have to do is, there's some interesting assumptions as I was rereading this. That are made about the classroom. First of all, when you give a task, everybody's working, right? Everybody is in a team that perhaps at a vertical non-permanent surface if we had it Liljedahl's way, but perhaps you're at a table, like a whiteboard table or using some other collaborative software like we'd be using, if you were doing this in a virtual environment, you might have a common whiteboard app that we use, right? Like we use Excalidraw, right? But the idea is you have a common space, and then when you're working on a problem and you get stuck, then what do? Right? Like the natural inclination would be to raise your hand and say, "Hey, I'm just gonna ask the teacher for some help." In an autonomous classroom, though, the response would be, "Okay." Instead of having the teacher be the sole authority in the room, the teacher gives up some of that authority and says, let's have you go take a look at group number 7, right? Team Alpha, right, or whatever. Pick your favorite, however you label, if you have like a
Team Sigma.
Team Sigma, right? And you can call them what the Sigma, right? That's the...
Correct.
Anyway, but you send them over to What the Sigma and say, hey, can you take a look at what they're doing? They're doing something sort of interesting. And you as the teacher are monitoring all the while and know that What the Sigma has something to offer, right? You may look at the work that Team Alpha is doing and being like, okay, you could benefit from seeing this. You invite them to go look at the other groups. And I think what would happen ultimately is as you start doing that more and more, teams will naturally gravitate to going to different groups. But then
right. Like you're modeling the behavior that you want your students to eventually have, right?
Yeah, you'd be doing this in the early stages of the classroom management, right? As you're getting the year set up. I imagine that you're going and setting those norms so that it's okay to go talk to others. And I can already hear some cynics in the room being like, well, hold on a second, my students won't do that. Aren't they just going to cheat, right? Like, isn't this going to be they're just going to copy off of another team? Like, well, one smart team, if you will, or one team that's very good at what they're doing is just going to be the sole source of information. And in Liljedahl's experience, that hasn't happened. Though I see why that argument might, there's this, I think that question at its core is engaging with what, with like the sense of doing things individually, of having individual accountability, right? How do we nurture this individual accountability when we are working in teams? And I'm assigned, for example, if I'm thinking about grades, how do I make sure that everyone gets a fair mark? Or how do I make sure that everyone has really learned the content that I want them to learn? And you might give individual assessments of knowledge throughout the year, but those are the everyday can be open group work. It's okay. And in Liljedahl's experience, the times where there's just copying is minimal.
That's one thing that certainly I struggle with at the college level is like formulating group work at the college level often leads to certain individuals not being accountable for like individual learning. And it's a struggle that I've had for a long time, and it's like I'm still a little uncertain how to address that particular struggle that we're having. Maybe it's just comes down to like setting norms earlier, right? And like what those expectations are. I'm not sure. So I don't know. Do you have any stories you can share in that realm, Zach?
I do actually. Because this is something that I remember. Are you familiar with Kagan? They're a cooperative learning group. They basically have a training company where they train people on cooperative learning. That's like the big
okay.
But
then no. I thought it sounded familiar, and then I was like, nope, that's not what I was thinking.
They had a U.S.-based program that I went through as part of my initiation when I was a teacher at one of my schools. And they talked about cooperative learning, and the training was very interesting. But they also gave us this big research book of like where all the practices come from. Like here's all the research for it all. And then I started reading that book, but it was really cool. The book was actually more enlightening to me because as I read it, there were these concerns about how do I hold students individually accountable. And I had the struggle too. I was like, I need to make sure that every student can do what they need to do. So what they recommended was when you do a group assignment, you have that group assignment that you all do, but everyone turns in something individually, right? And the biggest, the most interesting example of this that happened for me was when I did a geometry project where my students in a geometry class had to design like a campus, like a college campus, a mall, or some kind of big area using specific geometric principles.
Okay,
and they were able to make a common design. And I was trying to emphasize how to define words, like that kind of thing, and the use of precise vocabulary, because that's what geometry is all about. But as I did this project, I remember this one team, they did this project design, and the actual pretty cool actually. But I remember one student in that group getting an A on their project, and another student earning a D, the same group. And I remember thinking, like, the person with the D came up to me and was like, hey, how did you, why did I get a D on this project? And this person had done an immense amount of artistic work. I mean, you have to admit, like, it was probably one of the best artistic designs I'd ever seen in my life. And it was this thing that they had used in their group project. And what the student hadn't learned all the geometry, but had done the art really well, which is why the student had earned a D. Versus the other person had used the common design, but also was able to articulate the math, right? And so one thing that I do, ever since then, I've been doing a lot of individual assignments. Like I'll give, whenever I ask someone to turn something in, I will give a group project that they can all work on, but everyone turns in their own individual report.
Okay.
Right? Or another example, when I was in the college classroom and I did Calculus 2, we did group problem sets every day. And their participation credit would be their individual work uploaded to Canvas, right? So they would upload what they had done so I could see what they were doing. And every day before the next class would start, I'd take their work and analyze it. So I expected this to be uploaded like an hour before the next class, just so that they had time to, make it look nice if they wanted to. But in theory, someone could just take a picture of their work from the class period, upload it 10 minutes after class, and then I could start reading through those right before class to prepare. And doing that fostered a sense of individual accountability. It was rare for somebody to not get the points, but at least I could see that each person was taking some individual effort and had at least taken some kind of, ownership of learning individually.
And I guess even the act of like taking your rough notes away from class, rewriting them in a way before uploading them that makes them look nice, like to me that is individual accountability.
That's right. So you can have it, and Liljedahl gives several other options. It's all, but you have to actually ask individually sometimes. And I think that that's a very important part of this whole thing, is that yes, we have autonomy and we should have an open classroom where we talk about things openly and even let kids cheat if that's what it comes to. If you want to think of it as cheating, I don't think of it as cheating. If you literally give let the classroom be open for just inspection for other teams. Yet you do want to make sure that each person understands the content, and that's where you just have to separate those two measurements if you're going to measure for individual accountability.
I liked a lot of the discussion around knowledge mobilization, which is kind of what you were getting at in the last little bit that you talked about there, like students going to other, like groups going to other groups, and it's usually students going to other students, right?
Mm-hmm.
And I think you can develop a lot of. And the thing, like, I don't think that's cheating either, right? Like, if it's open group work and they're going to each other to look for the best way to move forward, even if it's not necessarily the way that they talked about it. There was one example that I thought was quite good in here, where I think it was like the two groups attacked the problem differently and came up with a similar answer. And so the teacher would say, okay, like, why don't you go through each other's work and see if you can make sense of their approach? Or the two groups that did the work similarly but ended up at different answers. Again, why don't you go through your work, make sure you're comfortable, and see if there is a mistake. So there were a couple like good examples of how to utilize that classroom dynamic here that I thought were quite good.
And really, a lot of this comes down to knowing your specific students. Because some strategies may work best in some classrooms, right? Like there are some, like, it's hard to be very specific. The general principle of autonomy is good, but I wonder if there are certain students that may need more scaffolding, right? If this is a new concept, I imagine that we are going to be, you might need to scaffold more and model a bit more for students what this looks like, what it looks like to have autonomy versus there may be some students who pick up on this really fast and are able to just move around to other groups just fine. And so like the autonomy is being able to use, I think as Liljedahl says, use what's in the room to your advantage, and like actually allow students to talk to each other. It's okay.
Yeah, I guess like the one big concern that I would have is potential disparity between students, right? So you have like students who tend to be higher performers. They get the advantage in this particular classroom of being able to teach the concept to somebody else, right? And usually by teaching the concept, you gain mastery over that particular concept. So I worry about the students that don't necessarily have that knowledge formation yet. maybe it's
Right.
good for them to hear stuff from their peers, right? But I think like if they don't quite get it, I worry that the gap between students might continue to grow. At least that feels like one of the things that should be
And
kind
let's
of
go.
addressed here, right?
Well, let's go one step further. What if a student says something wrong, right? Like, what if a student goes and says, this is absolutely, it gives some wrong mathematics and says that, epsilon is less than zero, right? Or something.
Right.
Right? Like, or it says, oh, well, let's let, if we, if they misapply the distributive properties, since I'm thinking about the distributive properties, since we're going to be talking about that in just a little bit, but if they show an incorrect version of the distributive property, what do you do as the teacher, right? Like, what if I send students to a group that they discover something wrong? What do I do about it? And his argument would be that things will be self-corrected. But I think you should take it a little bit further than that, because you as the teacher are also monitoring. If you see the wrong thing being said by not just one team but multiple teams, you might want to stop exploration for a minute and be like, okay, let's actually examine this work and talk about it as a whole class. That's one strategy. Like if it gets widespread enough, then you might say that's when you take control, and you may need to might need to consolidate a little bit earlier than you would normally do. Right?
We're gonna form a ministry of misinformation and disinformation in class, right?
And I wouldn't even go like, I know that like.
I'm just kidding, Zach. I'm just kidding.
Right? We're gonna have to make the and who's gonna be chancellor, right? Who's gonna be chancellor of the Ministry of Misinformation? The idea here though is, I know that sounds like it's direct instruction. It's meant to. It's not direct instruction at all. It's actually just having the consolidation early, right? All I'm doing is I'm saying let's get this out right now as a class so that we're on the same page. You don't have to go tell people stuff if there's misinformation in the room. You just need to help them see the logical fallacy and what's going on. If there is a misconception, right? If there's no misconceptions, there's no need to do this. But you just want to examine how widespread something is.
Well, I guess that provides you a lot of insight as the teacher too, right? Because if you're noticing that several groups have this misconception, then that means that it's probably a very common misconception in your students, and it does need to be addressed. And I guess too, like, we can't think about these particular tasks in a bubble either, right? Like, these tasks probably will be connected to follow-up tasks or other pieces in the curriculum where you're going to have a chance to address those misconceptions again, right? And correct those misconceptions.
Okay, well, let's take a look at our task from last time. Right, so what we were doing is we were trying to help students understand linear factoring, right? And last time we were talking about a lot of different question types, and today was more of a structural classroom thing where we talk about how to build the classroom for autonomy. I don't know that there's going to be too much that we apply here in that context, but I think what we want to do is, what we can note is that this task is set up to have multiple correct answers, which I think will allow for the autonomy to happen, right? For people to converge on a solution. If that makes sense. So the task is a good thinking task in that sense.
Yeah, and I think there'll be some there's potential for some competitive action here too, right? Like, oh, I found a bigger number.
Can I find the swap?
Can I find the next bigger one or whatever, right?
Yeah, right. Exactly. So, with that said, this is what we were trying to do last time. We created a snack platter with 192 M&Ms, 144 cheese cubes, and 108 crackers. We wanted to make sure that if we would like to make sure that we share these equally among our guests, how many guests should we invite? And what we did is we solved this, and the best way to do this is with 12. That is the optimal integer answer. We had a lot of debates about should we allow for fractional things, and I think we came to the conclusion the answer is no, though you could if you wanted to, but I don't think sixth graders would, since this is geared towards sixth graders, we wouldn't have many students thinking about rational numbers, except those who, are ready for that. And the task is designed to be an integer-only thing anyway. So we did that, and I'm not sure what else we had to do on this task. I think this is the the task.
This question felt quite good. I was thinking a lot over the last couple of weeks about how you might extend this to include negative numbers and what that prompt might look like with regard to negative numbers. Mm-hmm. I didn't know if you had any thoughts over the last couple of weeks either on this.
Well, okay, so if you're going to talk about negative numbers, go ahead and share your thoughts first. I want to hear what you have to say, because I have some thoughts, but I'm still forming them.
Yeah, for sure. I think the one that popped into my head over the last couple of weeks was you're trying to share some kind of loss amongst friends, right? So you want to kind of equally distribute that loss. Like, I don't know what kind of investing a grade 6 would be doing, right? But like I can see it at a high school level, certainly, where you might be trying to do some work and maybe you've bought this but it depreciated or you bought this at a loss hoping to sell it but you never did, and so you want to kind of distribute that loss amongst the friend group that did the investing. So that was kind of my initial thoughts.
Yeah. So here's the thing about that, because the first thing that came to mind when you brought this up about negatives is you need something that naturally is two-sided, right? That something has a positive and negative value that makes sense. For instance, temperature is a good example of that, or anything monetary, some kind of win or lose ratio type thing, right? Like if you had some way to handle that. And Jeff brings up a really interesting point too. Sometimes sharing is like we're defining sharing in a mathematical context as equal, right? Which is fair, but there are some who have different needs, and so he brings up correctly a disproportionate sharing, right? But distributive property assumes that we are giving everyone equal amounts. That's a part of the division, right? That's what division does. We don't say that 54 divided by 9 is equal to 7 or 10 or whatever, because like if we define division, for instance, as the largest quantity a group gets, then that could be very awkward and it doesn't feel as intuitive. Perhaps you could define a different operator that way.
And just with regards to Jeff's comment here, we could do valuation like 5 M&Ms equals a cheese cube. I think what we didn't want to do the last time we got together was have a connection between the different variable types. Otherwise, it's very tempting to just make a substitution and then do the division rather than actually work with the variables themselves.
That's right. And that's the point here was abstraction, because this is the first time that a student will see abstraction. We didn't want to have x equals some proportion of y, for example. We need to have some way to think of these in their own right as independent objects, disconnected objects. And so you might say that is linearly independent in the parlance of linear algebra, right? Like that these do not come together in any way. I know you are.
I know, but these are interesting questions. I mean, they will pop up, right? Like if somebody is lactose intolerant,
right?
If somebody brought that question up as a student, is that a avenue that we want to explore? Does it lead to anything that's interesting? And I don't know if it does.
No, I was going to say it doesn't feel like it. I think it confuses the issue more than helps.
Yeah.
Dessign also brings up an interesting point about when abstraction should be presented, and that's very like the definition of abstraction here is interesting, because to me abstraction is a progression. But the second you start saying the number 5 can represent something, or 5 can be just a symbol, right? 5 can represent 5 objects of any kind, or it can just be the symbol 5. That is already an abstraction that kindergartners make. So I'm thinking of 5-year-olds. So just in that sense, abstraction comes very early. But if you're talking about the algebraic abstraction, as in using variables for things, this is typically done in the U.S. about grade 6, which is, I'd say, 11-year-olds, roughly 12.
Yeah, but you're still building up to that, right? Like I remember in like grade 1 and grade 2, you just, instead of using X, you're just using a box.
Mm-hmm. Yes.
And right? Even, 1 plus box equals 3, and you're like, oh, well, that's 2, right? Because you're learning your addition facts.
That's right.
To me, that's still like some level of abstraction. You're just not using the variable X.
Right, but if you're specifically talking about abstractions with variables, definitely 6th, 7th grade. I didn't mean that on purpose.
Stop.
I swear I didn't do that on purpose. But that's just what the answer is, my friends. Anyway, as far as your negative question, Penn, because I think at some point we have to take off the training wheels of thinking about cheese cubes and crackers and so on. But we need more experiences with positive things until we get to negative things. We may have to punt the problem to just be an abstract problem in and of itself. But ultimately, you're right. We need to be able to say, I'll turn down the stroke width here, but, I need to be able to work with expressions like this. This is something that needs to be dealt with at some point, and even a -7. But I don't always have to do that with a context every time. Now, that being said, there are reasons to like, you can talk about skips and jumps when you talk about multiplication. I don't know if you've seen this before, but when you talk about integers. So, for instance, if I want to talk about -7 times 12, what I can do is I can start at my origin, 0, and I can say, all right, I'm going to make 12. I can think of this as 12 jumps of size -7, right? So I can go back this way. That's reasonable, and there are models that do that, but I'm using a number line and hops and jumps to do as a model. I've seen this done also with like temperature cubes. Like if you take 12 groups of -7 cubes, bringing down the temperature, that also could work.
This could be a good like algebra tile problem too, right? Like I'm just thinking about like a small example of like I have 3 positive things like this and like -3 x's. How am I going to distribute that to 3 people, right? Like you start kind of with these nice like simpler examples. Well, each I guess individual would get a -x and a 1 or something like this, right?
Mm-hmm. Mm-hmm. Right. But the idea here is that these variables they need to be independent, and they need to be seen as independent by students. That ideally not even x, y, and z, but we could use m, c, and r. Cracker using r and maybe h for cheese. I don't know. But the idea being that x, y, and z are those are just tradition. We don't have to use those. It might be useful to talk about others. I don't know. I'm also I'm actually reminded of something else. This comes from, so I've been using these for my problems of the week, each week. This comes from Secondary Math 1, so this was geared towards a 9th grade audience. But the idea was you had this cafeteria manager who counts all the things in her cafeteria and has, you have like people who buy salad in the lunch line, or people who, number of food servers and so on. And you can calculate stuff. So for example, I can look at A and say, well, that's S plus W plus C divided by C. So you have like the number of students that buy salad, sandwich, and pizza, and then divide that by the number of classes in the school. This would be an average, right? So the idea would be, what kind of expressions can I make? But I think this is more geared towards a high school audience, though my reason for bringing it up is maybe there's something we could do here with subtraction. Like it might make sense, for instance, to involve discounts or other things, while still recognizing that these are all measurable things. Or the discounts are like people who left the school, or I don't know, like there are ways you might be able to interpret a negative.
Yeah, food-wise, I kind of think about like you had this kind of like maybe you had to like throw out this many loaves of bread due to something, or right, like that's the first thing that popped into my brain. Yeah, I guess like from my perspective, is there more to do here? Like, do we want to?
I think we need to continue the progression somewhere. So this task would be a good first thinking task, but I think we need to build more. And let's go back to the objectives we set for ourselves that we had at the very beginning. I think that's important. So did we need it? Students will factor linear expressions using a common factor. Yes, we have done that. Students will conclude that the completely factored expression has a greatest common factor multiplied by a linear factor whose coefficient's GCD is 1. Yes, we have done that. We'll be able and the idea is to prove. We'd have to convince students and like work with them to show that this is the most completely factored form, right? That this, the 16, 12, and 9, we'd have to be convincing of like, okay, why is that the best? It's because 16, 12, and 9 don't share any factors. Common factors among all three. Because 16 and I like this because 16 and 12 share a factor of 4, right? Mm-hmm. But and 12 and 9 share a factor of 3, but altogether they share nothing.
Right. There's some similarities that might make you think that there's more you could pull out here, but there's not more, right?
There's not more. And I think that's a contradiction or some kind of that cognitive load, going back to cognitive load theory, that cognitive load of having to deal with three things, not having common factors is important, especially considering that one of the big learnings of 6th grade is about greatest common factors, at least for my experience.
Yeah, so it feels like we've met those particular objectives. Like, what would be the next step? So obviously the next step, I think, is just like more practice, bringing in the integer pieces. Okay. Like, is it worthwhile for us to kind of go into like how we might set up a quadratic factoring or something like that? Or go ahead.
So let's keep in mind our audience. Are we talking about having a 6th grade audience here? Because I think we are. I think we should stick with that.
Okay.
That being said, let's just look back at standard 6EE3. So apply the properties of operations to generate equivalent expressions. For example, apply the distributive properties to the expression 3 times 2 plus x and 6 plus 3x are equal, which we did. But we need to do more of that. And using that Mathematics Vision Project framework, they typically have some kind of develop, then solidify, then practice. Meaning that you develop an idea, but then you do more with that. Like make sure that it's really clear what distribution means. So what we've done is we've developed the idea of what distribution is, but we haven't really practiced or solidified it. And I think we need to do more with it. Like you said, put in some negatives, have some negative coefficients, have some other things that go on, because that will solidify in practice the idea we're trying to emphasize, which is distribution. Now, what we could do with that, in some ways we should give some more of the same, right? Like I feel like having these 192, 144, and 108 is good, but we need to have some, like it doesn't even have to be negatives yet. We could just have more of these positive things, because we want students to continuously come to this conclusion that the GCD of the coefficients is going to be the thing I factor out. That's really a big idea. So what other, maybe what we do is we vary these numbers. Instead of using 192, 144, and 108, what if we say, let's just change the numbers? What happens? Because I could see this being a next step for students. How do things change? And maybe we pick like 3 prime numbers eventually and say, what's going on here?
Oh, that's a good
Right?
idea. Yeah.
So what if I pick 3 prime numbers, like, not too big, but maybe something like 13, 17, and 23, and say, okay, I have 13 M&Ms, 17 cheese cubes, and 23 crackers. This contrasts, right? Because there's nothing I can do. So
Right.
and then it offers a nice, again, contrast to what students have experienced. So they'll experience this one where, I can factor out a ton of things. Now I have nothing I can factor out. What's different, right? And then maybe we have, maybe we also pick another. So let's take this and go with it. Let's draw somewhere. So, what about here for the numbers? What's that probability? Probably Orion. I had to read that carefully. But,
It does look like probability, and I got
It
excited.
did look like probability at first, and I caught myself. But how are you doing? We are going to chat about some numbers.
Here for the numbers, even though we are working with variables today. I liked your example. Yeah, 13, 17, 23. What if they decided to do 5 here? So if they decided to do 5, I'm just playing around a little bit.
23 crackers. Not the letters. Oh no. So if you said 3, 2, 3, 3, 2, 3. What's the context for 3, 2, 3? Are we looking at?
Oh, I'm just seeing I'm just testing some numbers that students might try. So let's say they tried to go, okay, well, I'll try to divide this by 2. Then you'd get 6 groups here with an extra 1. You'd get 8 things here with an extra 1. So I mean, this is maybe potentially a nice way to introduce like fractions too.
Mm-hmm. Well,
so
I could see someone trying to use fractions here, and you could factor out a 13 out of everything. And I don't even think we need to go to fractions. But more likely, this is really bizarre, actually, I think of this, but I wonder if one thing that students might try to do is just take 13 of everything out.
Oh, yeah, I see. Like, go like 13.
I could see them saying it would be M plus 4. No, just 4C and 10R. Right? That they didn't connect it to multiplication, that they see this as an additive thing. And maybe, like, this might be a bit of a long shot, but maybe possible. 13 plus 4 is certainly 17. So if I just, like, write 13 by 4...
Right.
Right? Like, if they're looking at this as a purely semantic thing rather than a mathematical object, they might say, I'm just going to write the 13 next to everything. So 13 plus 4 certainly is 17. So we could, you could imagine like 13M. This might be a bit of a stretch, but you do.
No, I could certainly see that happening. So how do you like?
Because like this, and then what you have to do here, is plus that C plus 13. This is maybe what someone would do. And like it gives you a correct answer, but then you have to go back and see if there was consistency. Because over here, then that would mean that 4 plus 36 is 40, which is less than the number of cheese cubes we had. Forbidden math. You could see a student doing it though.
I could see a student doing that, definitely.
Yeah,
because students, especially at this grade, think very additively and not multiplicatively.
Mm-hmm. Mm-hmm. And a lot of 7th grade focuses on proportional reasoning anyway. Like this is something that they're going to have to really engage with what it means to distribute. And the distributive property, when you talk about it in linear algebra, if you think about a vector space, you're taking 13, you're taking a constant and multiplying it across all terms, right? And factoring is the reverse process. It's like it's that equality when you have the left and right distribution. You have the equality can go both ways.
You forgot how you were taught fractions? Yeah, a lot of fractions for me were, I think, taught through proportions of circles and kind of like memorizing base fractions, if that makes sense. Like, this is what a half looks like. This is what a third looks like. This is what a quarter looks like.
Let's be honest, y'all learned it by pizza, right?
Yeah, seriously. It was all pizzas. Pizzas and cakes.
It's all pizza and cake. That's right. I actually like the cake metaphor better anyway, just because it's non-circular and it extends nicely to non-nice denominators. I find that you can generalize better with a rectangle than you can with a circle. Anyway.
This is one of those numerical questions where I think like manipulatives are super helpful.
Mm-hmm.
I'm going to pick some smaller prime numbers. I like 13, 17, and 23. But I could see a world where if you had like 3, 5, and 7, and somebody comes in and says, okay, I need to start now dividing this up. They might start by saying, okay, like let's make 2 groups and start like dividing some stuff up. And they might say, okay, well, that's going to be like, I got this, and I have like this leftover thing. I have like 2 in here and this leftover thing. And then what, 3 triangles in each with the leftover thing? Like I could see students doing this visually, and I'm going, okay, well now I just need to divide each of these things in half, and then we get our 2 equal groups, right?
Well, and to be even more clear, like if you had, let's see here, I'm trying to remember what I used as my variables. M plus, what was it, 2C and 3R. You'd write it like this, wouldn't you? You'd have an M, C, R.
Yeah, you'd be left over with a My Chemical Romance.
Mm-hmm. Right? And that's the thing. Like, this isn't, we know that's not factored, but how do you convince a student that's not factored? Right? It looks to me like it's factored, because I think this certainly is partially factored, but, sorry, it's a 2. I can't math. I'm sorry.
Oh, it's all good.
That's 2 groups. So, sorry, internet. So 2 of these, but then I have this extra term. And this extra term is our problem.
Right.
But again, very reasonable for a student to do that. So what would you do? You might say, well, did I divide everything amongst these 2 groups? And the answer is no, I've got these extra pieces. But and then they'd say, well, what about the fact that I have 1 of each of them? Isn't that worth something? And I'd say, well, yeah, but they're not split in these groups. So I'd have to then introduce either a fraction or say this isn't factorable over the integers, right? If depending on what you want the point to be, you could say, well, this is either not factorable, or you just have to make these cut each of these in half and then put half in each of these.
Yeah, so I think there's some very rich discussion here from using prime numbers, right? And you can take that, the GCD route, or I think you can also take this into the decimal fraction route very, very easily, which is why I like this prompt a lot.
Yeah. These numbers might even be too high. Like you're saying, 3, 5, and 7 might actually be better choices to go with the fraction route if you're going to do that. But here, I wonder, I could seriously see a student treating addition as factoring, which is not the same thing. Yeah.
And I guess that's where you utilize kind of group mentality here too, right? So like if there's a group that's going down that road, you can have them compare to what other groups are doing.
Exactly. So then we could have, we should probably change up we could change up our objects too. You know, say I have like, let's have one that maybe, 16 of something, and then how about 22 of something and 48 of something. I don't know, we can change up what they are. And it doesn't even have to be 3 things. We could have 2 things. So maybe I'm trying to think of what else we could use. You could use like a pen and I don't know, what else could we use? Chat, what are some other things? A pen and like Post-its. We have 22 Post-its and 16 pens. This one's interesting because
like, yeah, I was going to ask why you think why these numbers are interesting to you.
I think it's interesting. It's just to give students practice now. Like once we've engaged with the core, I need to multiply. I think it's just realizing that now I need to find a GCD of 16 and 22. So I need to have a whole bunch of you need some kind of practice to some extent without. Right, like I'm trying to think of some practice problems. Like what are some things that we can do? So some that are still interesting though, that vary things, right? Because you want to make the practice not repetitive, but you do want to make it repetitive enough that they can see a pattern. But you don't want to make it repetitive as in tedious. If that makes sense.
Mm-hmm.
So changing, for example, the fact that the GCD here is 2 isn't like the biggest thing in the world, but the algorithmic development of I need to look at these 2 numbers and find their factors and realize that 2 is the GCD is what I want students to see. And what we should do is have, just groups of 4 numbers.
Yes.
And this might be where we say something like, 10, I don't want to use 2 as a common factor again. Let's do like 5 and 55 and 30 and 100, right?
Sure.
But then, just so that we have like varying lengths, and I'm looking for GCDs of all of them. Oh, then I can see those are all multiples of 5. But ultimately, I think then we start saying, what if I start having negative items? Like, even if I start abstracting this away and say, let's just like pretend these meant something. What would it mean to have a negative number? We could still think about factors of a negative number. Eventually we'd want to divorce from context potentially, because that's, in some senses, that's what algebraic expressions are trying to do, is abstract away just formally. And so we maybe just have to punt on the real world part of this and say, what if we do this just as an abstract procedure? Once we've done enough of this, what would happen if the numbers were negative?
How do you feel about coprime numbers?
9 and 25, that's fine. Like, I think that's great.
Like, I think that's another interesting conversation, right?
Mm-hmm. So like
because they have prime numbers don't have any factors, right? So
that's right.
A clever student's going to look at 13 and go, well, there's nothing I can really do with 13, right? But they might look at 6 and go, oh, well, there's some factors there that I can try.
Exactly. So we need to have, I think that's another good example. 9 and 25, let's just throw both of those in there. 6 and 35. Because, like you say, they have factors that are not just one in itself. When you said coprime, I'm like, well, prime numbers are that. Like, didn't we already talk about that?
Right.
You meant it in the sense that there are more factors. I had to take do a double take on what you just said.
Yeah, because I mean, if we do want to connect this to the GCD, maybe the thought process of taking your numbers and factoring them is important, right?
Mm-hmm. Mm-hmm. And then you have like this list of 4. Then you have maybe some negative numbers that show up every so often. Just to say, hey, what would happen if I had a negative number? And yes, I could factor out. And this leads to some interesting things too, because I feel like in some ways this is its own lesson, and really depends.
The negative number or the
because you could have, imagine here That's fine. Or you could have this.
Right.
Both of these are acceptable. And so which one do you accept? Now, I think if we took a vote, like I'm curious, chat, what would you say? Would you say left is factored or right is factored? I honestly don't know what you'd say. I think I know what you'd say, but I don't honestly could see this going both ways. But which would you say is more factored if you
more factored? Yeah. What does that mean?
Correctly factored. No, like what's right to you? I think they're equal, but do you have a preference? Reading Dessignin's comment, when I was a teacher, other math teachers were surprised how fast I was going through the syllabus. I mainly summarized with ideas that you can derive through theories, which I doubt many students thought about. Yeah. I was more a mechanical student and was more comfortable with variables. I didn't feel like it's a thinking subject when it was presented with names and colors. I usually hacked the patterns and put together what I thought made sense. When I was in high school, I felt more comfortable with variables rather than real life names like cheese crackers. Yeah. I see. So Desant, like, it's interesting. One of my kids came home just recently. They were learning about slope and at school, and had basically gone through, like, in the lesson, they realized, oh, it's just y equals mx plus b, right? I just have to. My kid realized, oh, I just have to have a slope and an intercept, and I'm done. Right? Was able to hack the pattern that the teacher was trying to put in there. And some students think that way, right? There are some who, like you and my kid, who's like, I can figure this out real fast. And I think that's by design. Using crackers and cubes and cheese cubes and all of that is all just a model, right? In the end, we want the abstraction. And if there are some kids who can jump and hack the abstraction, that's sort of the point. We want that. I would love to have more of that as more mathematicians like that. That's literally what the goal is to hack the pattern.
And you get to use that to your advantage a little bit too as the teacher, right?
Yeah.
If you have a couple students that are there, it's like, well, cool. Now you can kind of like use those students to explain what they're doing to other students. Right?
And you can still challenge with something like this, right? 8, 9, -2, and 10, and be like, well, how come these aren't these the same? Which one? How do you determine which one's factored correctly? Raven says left is the more correct one. I tend to agree on this one. So Chad, if you have any other thoughts, like, I think the left one personally is my favorite, but of the two. But this is something you could bring up, and I wonder. See here. Go ahead and you're writing it down for everybody. Which one is?
Which one's more advantageous now?
Right.
Exactly. Context is important, right? So, like, I think both of them have their place, certainly.
Yeah. Just imagine the crackers in X-shaped or X-shaped. Shaped? Is that shaped?
The crackers are X-shaped. Yeah, I would buy X-shaped crackers. We buy goldfish-shaped crackers. We need algae crackers. We need X and Y shaped crackers.
That sounds glorious. Can you imagine? I mean, solving for X with crunch or something like that. I don't know. Like, gotta come up with some really clever.
You're thinking of like the tagline.
Tagline.
That would be amazing.
Not AI generated, by the way. Contrary to what people think, right? I'm not AI. I'm waiting for Jeff to come chime in and be like, actually.
If there are any investors out there that want to, start algebra crackers with me, just let me know.
Okay.
Numbers you can really crunch.
Yeah. Exactly. Yeah, probably, Ryan. Yeah, you got it. You got the idea. But yeah,
we'll throw some numbers in there, throw some X's, Y's. Yeah, we're good.
Yeah. That could be really fun, actually. I can see that going to town. So yeah, the idea here would just be to generalize the concept of a GCF to factoring and writing it down using the notation. Because that's what we really want students to do, is not only notice the GCF, but to write down algebraically this pattern, right? The thing we haven't talked about, which we probably should, like once you see this pattern, we should probably address the concept that there are going to be some cases where you just have something like this, where you have because ultimately what a sixth grader will learn is needs to learn is how to factor something like this, negative 10x plus 5, right? Where you have a linear, it's truly linear in the one variable sense, and we have a constant. And so I think this is just done abstractly. At some point we have to just say, all right, now we're going to look at expressions that have a variable and a constant. You could think of this in the same way we did, where you have 5. Maybe this is where we throw in money or something. I don't know, but just like 5 somethings, and say, okay, I have 10 of something and 5 of something else. In some ways, the model still works, but I just have to realize that a constant is treated as if there's no this variable is ignored. There is no common factor of x here that I can factor out. I'm garbling my words here, but I'm trying to just say students need to be able to engage with this. And what will probably happen, what has happened in my experience, I shouldn't even say what probably will happen, I guarantee you what will happen, is that students will do something like this.
Right, they'll ignore the constant.
They'll ignore it. And we need to perhaps this does need context, right? I wonder if this is a time to use money, is to use it for when we have a constant.
I mean, what did we have up top here, right? There was nothing saying that we needed to use variables in any of the questions that we've looked at. So even your right, like how is this really different? Like at the end of the day,
right.
I have 10 of one object, I have 5 of another object. That's really all we're saying. Whether or not those objects are x's or y's or constants, it's kind of the same, right? So I feel like there's a way we can set this up and say, like, 2 groups took this problem and solved it. One solved it this way, one solved it this way. Anyway, you sound like you wanted to add something here.
No, you're fine. I will say, though, in addition to that, you're absolutely right. The difference here is that we have this lone 1. And knowing that 1 is the factor that's left over when everything's been factored out, that isn't obvious. That's why I'm saying I would expect a student to say something like this. Like, just psychologically, you would expect a student to do this. Maybe even leave a little space. Right?
Right.
Either just put, or even like this, you can see a 2x plus and being like, well, okay, I factored out the 5, and I need to make it clear to the student that there's this 1 term that's left over, that's the thing that's left over once I'm done factoring, which is a naturally multiplicative thing. This is the multiplicative identity, as we say formally. But I want the student to be able to realize that 1 is always left over. And so we would have to design something that would say that that I can have 1 as a factor, and that's okay.
Yeah, what are we saying here? We're really just saying that if we were to create 5 groups, there should be 1 object that's distributed to that group, right?
And see, yours is really interesting. The example you're saying, it's functionally equivalent. I sort of agree, but we don't run into this issue of having nothing left over, right? The difference here is I have, like, structurally speaking, if I'm looking at this semantically as strictly a string of symbols, which I'm doing algebraic manipulation on, I'm taking the 5 out and moving it out. I'm thinking of the 5 and the y as distinctly different things. Whereas here, this 5, if I treat this as a factor, I don't know what to put in its place. It's like I'm literally moving it away. And so the multiplicative identity needs to be like squarely in the kid's mind in order to know to put a 1 there. Yeah, 10 gold. Yeah, right. So if I say that there's if I have 5 people I'm going to share this among, then each person gets 2 gold bars and $1 bill. This is why.
Right, and maybe that is enough of a connection back to your 1, right?
Right.
But I could also see it being solved this way too, right? Where some student might set it up this way and get this.
Right.
And maybe I set it up in hopes that people will solve this slightly differently and they can compare notes or something like this, right?
If there's anything I've learned, it's that you don't solve it by hope. You don't design it by hope. You don't understand by hope. You understand by design.
You don't design it by hope. Okay. Yeah. We
Right?
we don't hold on to hopium around here.
Yeah. No illusion that hoping will work. And so we need to be intentional about how do we attend to the number 1 being the multiplicative identity, the thing that is left over when nothing's left after factoring specifically.
Well, is it worthwhile to put students in no hope? Is it worthwhile to put students in a situation where we do it in the forwards direction first?
Maybe.
As a reminder, okay, like we've done this already, this distribution in the forwards direction.
Oh my gosh.
And then put them in a situation where they have to work backwards and see if they can kind of connect the dots.
Yeah. I think that might be the way, right? Like maybe I don't want to just drill that away though. Sorry, there's something like this. This is the traditional rainbow method, which the whole design of what this original task is to do is to get away from algorithmic thinking of just like doing. I don't want students to have a limited view of what the distributive property does, right? Because what ends up happening later on, if you have a limited view, is I'm going to go over here just a little bit off the screen and previewing what could happen. When you talk about factoring trinomials, the mnemonic is that you just use FOIL, right? First, outer, inner, last. And that works, except when you start talking about things like, a difference of cubes, for instance. So if I do something like this, then the first, outer, inner, last thing breaks.
Right.
For example. And this turns into x cubed equals, or minus 125, right? So what I'm trying to do is make it clear that when we distribute, we're distributing each term in group 1 with each term of group 2, and specifically by multiplication, and taking all of those products and summing them together. When I come down here, like the 5 times 2x plus y is much more what you'd expect a 6th grader to engage with, but it's what am I trying to say? When people teach FOIL, they should be clear it's strictly for multiplying. Exactly, megalomorph, exactly. Like this is the other example I think of, and I'm being a little bit more advanced here, right? But I think it's relevant. When you factor quadratics, but that require complex numbers, and they have complex roots, you'll often have trinomials multiplied by trinomials. And I think this ends up being x squared plus, 16, 9, that's 25. Did I do that correctly?
All I know is you're saying trinomial, and I see that as a binomial.
Okay.
I'm just kidding. I'm kidding.
I know. It messes with me, dang it.
But I know what you mean, right? Like this idea of having to take... You're basically finding every possible pair or every possible combination, right?
Mm-hmm. What is this? I'm trying to remember how to multiply complex numbers in my head. Because you get all the stuff that cancels. We get plus 9. Gosh. I feel like I'm off my...
And you should get a plus 16.
Off my A
right?
game. You get a plus 16. It's not 25, though. There's some other term here. What am I missing, chat? Is it...
You're going to get a minus 6x too, aren't you?
That's what it is. Yeah, that's what I thought was missing. Yep, was 25. There you go.
Yeah, that looks right.
I think that looks right. Okay, I was finally getting the negative 3x twice because I think that's the ones I was missing.
Yeah, I know they're always a little weird. The dealing with complex numbers.
Yeah. Doing this on the fly, by the way, chat. I'm doing this. This is not scripted. We purposely don't make this show scripted because it's not as fun that way. But
yeah, I mean, Megalomorph has a good call there, right? You can kind of think about it as x minus 3 squared, I suppose, right? Plus that.
That's right. That's right.
Yeah, because you do have a difference of squares, and the if you group the x minus 3s, you have a difference of squares, right?
I was just making sure that we had conjugates because that's what we're supposed to have. We did it. Yep, x squared minus 6x plus 5. There we go.
Yeah.
I just wrote x squared.
We did it.
Yeah. Thank you, Megalomorph. Yeah, I mean, you can see that as difference of squares, I suppose, if you like. But my point still stands that when you want to make sure that when you set up students for success, even early on, and you don't, when you generalize something, you don't want things to break.
Yeah, like this, I agree with Megalomorph. Like the first thing I see here is this kind of area model for multiplication, right? Like, and that might help clarify some stuff. I just don't know how you bring that into the conversation like easily, right?
Well, you suggested algebra tiles, and that works. We can use those, and I think that might be where we have to go. No, you're talking about this, Megalomorph. I think you're right. Because, like, you can... Right? And we did this in college algebra when I taught it. Right, so you have your 6x. This is what I was doing in my head, actually, when I was doing this. And then this one is 16i squared, negative 16i squared, which is plus 16. It turns out, because these are conjugates, this term and this term will be negatives of each other always, right? And so they make 0 together. And similarly, this term and this term is a conjugate of each other, so these will be 0, and we just add these things together. It does generalize nicely, and it even generalizes nicely for what's it called? For division. Like when you divide polynomials, you can actually use this to divide if you wanted to. There's some fun things you can do with that. But I think we've done what we can right now. This is just a puzzle to think about, like this one. I feel like this is something I've encountered with students repeatedly, that I've really just been like, how do we intentionally design for the one, being the only factor left over?
Yeah, and I think you're right in that, like, maybe imbuing some of the algebra tile or imbuing some of the area model throughout this might be helpful in resolving that problem. But I'm not sure my intuition has like a specific example that's going to just enlighten everyone that this one has to be there, right?
Yeah. And I think what we have to do, I think that's just something, if we bring in the algebra tiles as a connective tissue, so like once we've done these tasks here, we can then start using algebra tiles as a way to generalize this stuff, right? We can treat the algebra tile as our variable. And I think once we start, this would solidify the procedure we want after we've gone through these examples down here with 16 and 22 and co-prime numbers and such. Once we've done that, then we can jump over to practicing, going through that develop, solidify practice. I would practice with algebra tiles and say, okay, now that we've developed the concept of what distribution is and we have a correct understanding, now we can practice with algebra tiles and be specific about using X and a constant, and then generalize or apply the procedure specifically to that context, which is ultimately what students need to be competent with anyway. Like if you look at the standard, that's a lot of the examples are in this vein.
Right, and to me, a lot of it just boils down to like these kinds of models. I think are helpful, right? Like these area models, or like to me, I also like the group model a lot, where you kind of like just share things, like because all we're doing is like a fancy division or a backwards fancy multiplication, right?
That's right. And the nice thing is with the practice, you can do this last part of the standard where you have y plus y plus y equals 3y. This is another example where you have like these hidden ones, right? And so I can then say the 1 plus 1 plus 1 is 3 and make that explicit. That's where I do that in that practice with the algebra tiles, so that we realize, okay, these algebra tiles are much like my cheese cubes. So, but now I just have abstract things rather than working with.
I have a question for you, Zach.
Yeah.
I think I know your answer, but I'm going to ask it anyway.
Do it. Ask the question.
Do you ever see that? And if so,
Never.
What do you do?
I never do. I wish I did.
That's so
actually.
Interesting. I see that a lot. I see that a lot here.
I never see this. That's interesting that you see it, because I wish this were more of a thing that people would say. Because then this actually, to me, even though on a test people would mark this wrong, and I think that's absolutely wrong that they do so, but I feel like this actually shows a deep understanding of what's left over. Putting the one there, even though conventionally we don't do it, it's something that tells me you understand that there's this multiplicative identity that exists. I think that's really good. But if you were on a standardized test, this would mark it wrong because it's not convention. And it's hard to, do I accept this? Even more awkward, right? If I wanted to be awkward about it.
I want you to be awkward about it.
Do I accept this just to be...
Oh yeah, with the numbers
cursed.
At the end.
This is cursed. But like,
yeah,
you never would do this. But like,
I've seen that too.
Yeah, I've never seen that one. But if you did, wouldn't that be interesting? I again, it shows understanding. You never see it. At least I don't. If you see it, that's awesome. I'm actually really happy you see that, because I do not. But this is cursed in my opinion, just because it makes my inner mathematician cringe, but it's still something that is valid. I mean, you can't knock it. It's just not convention. But get that cursed image off the...
But it comes back. Like it'll come back, when you're doing your like working with complex numbers. Like, do you do 3 plus 4i, or do you do 4i plus 3? Like,
that's more forgivable though, right? Like I feel, because it's like how you say some people will say, I square root 2. Or will you say square root 2i?
Oh, I hate writing root 2i because I'm worried that it's underneath the...
It's that vinculum, right? Like that little thingy. That's the fun word to say, by the way. Thank you, James Tanton, who taught me vinculum and uses it often. You should know that word. It's on the test somewhere.
It'll be on season 2's test.
Yeah, season 2 test, guys. Vinculum, that's the word. That's the word for the little bar above the radix of the above the radicand of your square root. So, vinculum it is.
So I don't know how you're feeling, Zach. I feel like we've kind of tidied up some of the leftover pieces. We've left a couple of threads for people to think about with regards to setting up this task. Where do we go next? Like what makes sense to do here during February?
So in February, I think what we'll do is I really want to come back to this +1 thing and really develop it with algebra tiles.
Okay.
And then when we come back, what we need to do is talk about consolidation. Yeah, Dexy, that's awesome. That's why you put parentheses. That's what it's there for, right?
True. Yeah.
True. So what I would do is...
Hey, Tans. How's it going? Welcome in.
What's up? Hey, Tan Squirrely Mans. we are chatting about building thinking classrooms, and go ahead.
Dexy, if you're here and you want to give Tanza a shout out, feel free to do so. Otherwise, I'll do it after I put the book down. Is Consolidation Chapter 9?
It is Chapter 9. That's right. So we're going to talk about that, and I think we can consolidate this whole unit into, we can take this sequence of this problem string and use this as an opportunity to consolidate. Like, we can sort of model what consolidation might look like for this mini unit and closing out our unit, right? Closing out this little mini unit on factoring.
Yeah, no, I like that a lot.
And then after that, we'll let you know what's going to happen next, because we have some other chapters we'd like to talk about. But we're specifically going to be looking at Chapter 10, right? Is it 9 or 10?
Yeah, I want to read 9 and 10. I think 9's interesting. It's like how you like give hints and like order that structure through the flow through the classroom. I think that's also kind of interesting. Mm-hmm. But 10 is the one you want to focus on, I think, which is the consolidation piece, right?
Yeah, and we can talk about that. We'll 9 and 10. If you read both of them, if you're happy to read it along with us, read them both, and we may spend the next 2 meetings on those 2 topics: how to give hints and how we consolidate. That will be the month of February.
Sweet. No, I think that's a good plan for February. So you and I would like to meet with you before the 12th of February. So I want to do Zach's suggested reading, and then maybe we can formulate a little plan of attack for when's our next episode will be on the 12th of February, and then the 26th of February after that. So it'd be nice to chat before the 12th and get a little bit of a game plan for kind of just some of the discussion points that we want to chat about. I know that we like keeping things a little fast and loose.
No, but we do also we have a structure here. As random as it seems, we do have conversations about what we're going to be doing over a period of time. So like I'm not making this up completely. It does have a plan. It's just we have a very loose plan, and in some ways that's a good thing, in my opinion.
Yeah, like I'm pretty sure our plan for this particular episode was, Zach was like, why don't you read Chapter 8? And I was like, cool, I'll read Chapter 8, and then we'll talk a little bit more about the factoring task. And he was like, yes, that was our plan. But it's good. I think like it lends itself to a very open and honest discussion, right? And it's not really scripted.
Yeah, which is. And I'm good with the with what we've talked about. Thank you all for being here. All of you that do this and join us for these. It makes my day, and I appreciate being able to banter with Penn. And we do need to make algebra crackers a thing. I think that should be definitely. That sounds like a thing waiting to happen.
Yes.
Some investor out there has an opportunity waiting to.
It's true. It's true. We're gonna make it happen. So if there's like. If there's a financial investor, like, if one of the sharks is watching this stream and you want to invest in algebra crackers, like Zach and I are your people. We'll make it happen.
I'm looking at you, Mark Cuban. It's our you're our only hope.
So I'm actually going to stay on stream. So I'm going to take a small break just to use the washroom and get set up for part 2.
Into the mouth.
And Dexy, start the phone. Look at that.
Thank you very much for the biddy donation, Dexy. Yes, that is exactly what algebra crackers would sound like. Delicious. So I'm going to take a small break. I'll be back. I want to do a little bit of work with getting the Euler phi function set up for my encryption class. So I'll be back probably in 3 to 5 minutes. Just give me a little bit of a break. But Zach, maybe you can let people know when you're streaming over on your channel and what's upcoming for you.
Well, we're ending January, so question and answer session Saturday. Bring your questions. You can join Discord. You can ask a question there, and I'll try to answer it. And then after that, we are going into February. We've got of course, the podcast, but I've also been working on some problems of the week. We got a new hot set of problems of the week just off this morning, hot off the press, and you can go work those. And maybe we're looking at. I'm looking at ways to be able to give rewards to people who help out with these too, because people have been very generous with providing solutions and allowing me to talk about them on stream. So I'm working on a reward system stay tuned for that.
Free algebra crackers.
Free algebra, if I can get it out there, right? Like, if we get this thing, that could be really fun to make the algebra crack. We need to make that a thing. Thank you so much for again joining us today, chat, and we appreciate you all. Thanks for the discussion. I'm gonna let Penn get over to doing some encryption and all that kind of stuff, but I'll be lurking and I'll probably troll Penn as he goes.
Please, yes,
that's probably what I'll be doing. So we'll catch you later. Thanks.
All right, thanks, Zach. We'll talk to you soon.